Hi guys, today we would like to discuss motion in circular path. When we are moving in circular path, we need to learn so many things for the safe clear of the turnings. Sometimes we need to bend in proper way so that we can clear the circular track. Suppose if we do any wrong to clear the circular track, we will be out of the track. So by applying proper physics knowledge and by understanding what should be done while traveling in circular paths. So today I would like to discuss such very important necessary things, how to deal with the motion in circular paths. So for that you should know from the very basics. So I would like to recall your basics. The first one is that when we are moving in a circular track, so we are having an acceleration. So that acceleration we call as centripetal acceleration. So the object which is moving in a circular track, so having an acceleration, suppose if I take this is circular track, so the circular track is having a radius. It is not necessarily a circle, just like a curve having a radius. So just like this track you take. So suppose if this track is having a radius of r. So if we are moving in the circular track, so the object which is moving in circular track, which is having an acceleration which is known as centripetal acceleration. So the formula for the centripetal acceleration A equal to v square upon r. Here v is the velocity of the object and A is the radius of the circular track or radius of the curved path. So here v is the linear velocity. Here v is the linear velocity. But we need to convert that linear velocity to angular velocity, and we know expression the relation v equal to r omega. So this is the relation between linear velocity to angular velocity. If you can substitute at there, so acceleration A equal to, the expression changes as r square omega square upon r. So if you can cut r, so in r square 1 times the final expression for the centripetal acceleration, the centripetal acceleration A equal to r omega square. So this is the expression for centripetal acceleration. If this object having centripetal acceleration, the object having centripetal force, centripetal force, we know that force formula F equal to ma. So in the place of A we can substitute A equal to r omega square. Now we got that centripetal acceleration formula. So the centripetal acceleration, the centripetal force F equal to m times r omega square. Or this also you can write that F equal to mv square by r. If you can substitute v equal to r omega, so in this expression, so we can get that F equal to mv square by r. So the centripetal force, if the object is moving in a circular track, so that object having centripetal force. So remember that centripetal force. centripetal force F equal to mv square upon r, or which also equal to mr omega square, and centripetal acceleration A equal to r omega square. So this is the previous knowledge we need to have to understand further. So when you move in a circular track, and especially when you encounter turnings, the left turn and the right turn, so we need to lean or we need to bend towards to the turn. Suppose if this is straight track, so there is no curve at all. So the forces which are acting, so right now the forces which are acting, so the downward force which we call as mg, which should balances with the upward force, normal action force. So I can write an expression r equal to mg if we are moving in a straight track. So the forces are balanced, so that's why the bike is stable. But when we encounter turnings, so this is the turning. So when you take the turn, so in this case what happens, the normal reaction force will change its direction because of the turn. So in the earlier case, the normal reaction force, which is representing in red line, is straight, or if you can take a back, so this is the earlier case, the normal reaction force R is exactly balances the centripetal force. But when it comes to turns, now the R has changed. Now the normal action force has changed, but the weight is do not change. Weight is mg, which is the downward direction. Now it depends upon the angle. Now we have to resolve the normal action force into components. If this is making an angle theta, suppose if I take this is an angle theta, if the bike is making an angle theta at here, so this component will becomes r cos theta component, and this component becomes r sin theta component. Now the r sin theta components and r cos theta components will balances in this case, but in the earlier case there is no components at all. But when you can take turn, so it depends upon the turn, whether it is a left turn or the right turn. So it depends upon the turn. So the bike has to bend. The bike has to bend in such a way that to balance the centripetal force. So let us try to learn the bending of a cyclist or bending of a motorcyclist. And moreover that, it's a common sense that the friction which is supported by the road is also matter while we are dealing with the circular motion. Let us try to derive an expression for bending of a cyclist. When a cyclist goes around a curved path, a centripetal force is required because of the curvature. So the force of friction between the tires and the road is too small to provide the necessary centripetal force. So here friction do not help us at all. Again I am saying the force of friction between the tires and the road is too small to provide the necessary centripetal force. So that's the reason the cyclist going around a curve. Cyclist going around a curve leans inward. Depends upon the direction of the curve. So he leans inward towards the curve. Because the horizontal component of the normal reaction provides the necessary centripetal force. So as per you see in the free body diagram of a cyclist, so this is the case A when it is moving in without a curve. So but when it encountering a curve, so the figure B, so the normal reaction force is resolved into two components. So those components are sine theta component and another component is r cos theta. Depends upon the angle, so we resolve the normal component of the cyclist. Now from the figure you can write that suppose the cyclist bends, bends inwards through an angle theta. Suppose the cyclist bends through an angle theta, then the normal reaction force resolves as, from figure, I can write that r sine theta. First I will write that r cos theta. From figure, r cos theta, which is equal to mg. So let it equation 1. So this r cos theta is a vertical component of the normal reaction, balances the weight of the cyclist and cyclist. So mg is included weight of the cycle plus weight of the cyclist also. And the vertical components is balanced with mg. So the horizontal component in this case goes to r sine theta. Now the horizontal component of the normal reaction should provide necessary centripetal force. So without centripetal force, we cannot complete the circular motion. So the horizontal component or sine theta provides necessary centripetal force. So if you can make it equal, the horizontal components, then the equations will become as therefore r sine theta which is equal to mv square by r. So this is the expression for centripetal force. Now if you divide 2 upon 1 to get the expression for centripetal force, so r sine theta upon r cos theta which equal to mv square by little r upon mg. Now cut the like terms on both sides, r gets cancelled and mass gets cancelled. So the remaining expression is sin theta upon cos theta, we write that as tan theta. Tan theta equal to v square upon rg. So from this we can write that theta equal to tan inverse of v square upon rg. So how much how much the cyclist should bend without fall. How much the cyclist should bend without fall. To calculate that, how much angle the cyclist should bend. So that angle, if we can take that angle as tan theta, so the angle is purely depend upon the following factor, that equal to v square upon rg. So here v is the velocity of the motorcyclist, is the velocity, and r is the radius of curvature, or the radius of curved path. Now the angle theta is purely depends upon this following factor. So without decreasing the velocity of the bike, to clear the curved path, we should take an appropriate angle. Otherwise, we know that to clear curved path, we need to decrease velocity. Otherwise, there is no necessary centripetal force we will get. But without decreasing velocity of the motorcycle, so to clear the curved path, we need to bend. So that angle is purely depends upon the velocity of the moving object along with the radius of curvature or radius of the circular track. So this angle is necessary angle to clear tan theta equal to v square upon rg. So this is all about bending of cyclist. So if you can think about what about car. So to the car, is it necessary to bend like that? No, to car it is not possible. So we will learn that how it changes to a four-wheeler.